To derive the small dipole antenna from a Hertzian dipole, which you can refer to in previous videos of this series, we go from the analysis of the Hertzian dipole, which is the following. We had an expression for the electric field of R. We had an expression for the magnetic field as a function of R and theta. And the difference between the magnetic field and the electric field is a characteristic impedance Z0. From there, we go ahead and obtain the Poynting vector by multiplying both of those and taking the real part and dividing by 2. And then from there, we integrate over the surface of the sphere and come up with this radiative power expression. From the radiative power expression for the Hertzian dipole, we go ahead and note the following. That to go from the Hertzian dipole also known as the infinitesimal dipole, to the small dipole, we replace I naught with I divided by 2, or the average current. So in this case, we end up with P radiative equals to Z naught K L squared divided by 12 pi times I divided by 2. So we see a factor of 4 coming into play right there. And P radiative, or radiation, equals to Z naught K L squared over 48 pi times I squared. Similarly, you can get the expression for the electric field for the small dipole. Like we said, you divide by 2 because you're taking the current divided by 2, the average current. And then the magnetic field, the Poynting vector, can also be obtained in this way. One thing to note is that we usually go ahead and express, for sinusoidal currents we can do this, have an expression for power, which is the following. P naught equals to 1/2 times the radiative resistance times I squared. If we set that equal to our expression above, I squared, we can go ahead and do some simplifications. That 2 comes over here, that cancels with that, and we get 24. So then our final expression for radiative power is equal to Z naught K L squared divided by 24 pi. Now, go ahead and put that in a red box and note a couple of approximations, but definitions that we can make here, and put this in a form that you might have seen in different places. That would be, if we go ahead and notice that Z naught is the characteristic impedance of the vacuum, which is mu naught over epsilon naught square root, and computes out to be 377 ohms. And K is the wave number, or 2 pi, divided by lambda. If you go ahead and replace that here, replace that into the squared there, this gives you the radiative resistance in terms of the length of our dipole and the wavelength of our antenna equals to 20 times pi squared times L over lambda quantity squared. This is the expression as you find it in many places, and that's how it's derived. That's how it comes about. And both expressions are equivalent, of course. One just goes ahead and does a lot of the number crunching for you. So it's an easier, possibly an easier way to remember using that pi squared term. And that's the conclusion of this video.